So, building a climate laboratory, how climate models have revolutionised our understanding of planet Earth. But I'm going to start a long way back. I'm going to start with the very early stages of climate science, because by doing that, I think we can understand a little bit about what climate models are and why we need them. And because we're here in this historic place, it seemed only right to start with what is, for this country, a very distinguished record of history in climate science. So I'm going to start with Edmund Halley. In the early 18th century, he wrote a rather interesting paper that appeared in the Philosophical Transactions of the Royal Society on the trade winds and monsoons. And in that paper is this really quite iconic map that he drew of the winds of the tropical oceans, where his dashes indicate the direction of the wind, and where you can see there's some fine dashes, much smaller dashes, particularly over the Indian Ocean and up into the South China Sea and so forth, where he'd noticed that the winds changed direction as you went through the season. So this is the monsoon. And this, of course, reflects the British Empire as a trading nation, a maritime nation. And so here we are, here's his depiction of the trade winds. And he puzzled about why they always blew, they were always easterly winds, whether they were northeasterly or southeasterly trades. And what was the physical cause of that? And of course, he had no way really of unpacking that, because this is just an observation. And he hypothesized that the passage of the sun around the equator led to, as the sun went past, the air was heated, it rose, and it pulled in the air from behind it. And as the sun was going in that direction, it would pull in easterly winds. And there we were. So he just thought that it was part of the diurnal cycle, the passage of the sun around the equator, that caused these winds to blow from the east. But of course, you have to wait then quite a few more years till you get to George Hadley. Nearly 100 years later, here's George Hadley talking about the Hadley circulation. And he talks about how the air, as it moves from the tropics towards the equator, having a less velocity of diurnal rotation. So here we are now already accepting that the climate of our planet is determined by the rotation and the rotation of a sphere. And so he argued that as the air moved towards the equator, it having a relative motion contrary to the, so that when it reaches the equator, it has a relative motion contrary to the of the Earth in those parts, which being combined with the motion towards the equator, a northeast wind will be produced on this side and a southeast on the other. So here he's talking about conservation of velocity. And that's where it stayed for actually, again, quite a long time, until we get to Coriolis, who was looking specifically at the motion of an object in a rotating frame of reference. Of course, highly relevant to the atmosphere. And it was Ferrel in particular that picked this up and realized that actually in the rotating frame of reference for us sitting on the planet, if a body is moving in any direction, there is a force arising from the Earth's rotation, the Coriolis force, as we call it now, which always deflects it to the right in the northern hemisphere and to the left in the southern. And of course, that effectively explained not only the trade winds, when you moving air from further north towards the equator, but also why we have westerly winds at our latitudes. In other words, superrotation of the flow. And so he was the first person, Ferrel, that recognised that the conservation of absolute angular momentum was fundamental and not absolute velocity, as Hadley had assumed. So here we are into the 19th century before we have really an understanding of why the winds, the basic aspects of our climate, are to do with the fact that we live on a rotating sphere. And that explains, and the speed of rotation and so forth, explains a lot of the atmospheric winds that we observe in our climate system. And then the next great breakthrough really only came in the 20th century with this man, Carl Gustav Rossby. And here, he's actually taking this a step further, because not only are we on a rotating sphere, we also live on a sphere that's heated at the equator and cooled at the poles. So we have this idea of a temperature differential between the equator and the poles, and also that our atmosphere is stratified. In other words, there's a temperature gradient as we go up through the atmosphere. And he combined these and recognized and showed mathematically that you would get preferred wave motions in the particularly around what we now call the jet stream, which separates the very cold air over the poles and the much warmer air over the equator. And the diagram that we can see here is just an example of the evolution of what we often now call the jet stream, or the large-scale waves in our atmosphere, through a sequence of events where that jet stream actually starts quite symmetrical and then becomes gradually more buckled until these waves break, and then we go back to a more continuous flow. And we see these every day when we look on our weather charts, and you often see the forecaster now talking about the buckles in the jet streams. These are the Rossby waves that determine very much the regional structure of our climate, and they're there because, first of all, the rotation of the planet, but also the heating differential between the equator and the poles. And these waves are absolutely fundamental for how we move heat from the tropics, where the planet is continuously gaining energy because it's closer to the sun, to the poles, where it's continually losing energy through particularly the loss of heat. And so these waves are how we equilibrate the equator, the temperature structure that we now recognize as our climate of the warmer tropics, the colder poles, but a certain temperature variation between the two, very much delivered by these what we call planetary scale waves and the weather that grows upon them. So here we are, quite late on, 20th century, and the theory, the foundations of what we now call dynamical meteorology. I've talked about the atmosphere, but of course the same things are going on in the oceans, which is also a fluid on a rotating sphere. Of course, the ocean's a bit more interesting in the sense that it's not a continuous fluid. It's bounded by the shape of the continents, and so the ocean flows behave somewhat differently from the atmosphere in their characteristics. So here we are, some very basic stuff. That's the dynamics, but let's step back again to Tyndall now, back into the 19th century, and think about the thermodynamics, and particularly the radiative properties of the planet. And it was Tyndall that first proved that the Earth's atmosphere has a greenhouse effect. Without the atmosphere, without the way in which the atmospheric gases absorb and re-emit thermal energy, thermal heat, we would have a surface temperature that was considerably lower than the one that we have today. And indeed, life would have a bit of difficulty thriving in the way that it does today. So here's Tyndall. He's beginning to understand now why the planet has the temperature that it does. And he also showed, important, that these gases were emitters as well as absorbers of infrared radiation. So we're beginning to see the beginning understanding of the greenhouse effect. And here's the first prediction of global warming. by Arrhenius, again, not that long after Tyndall, and it's interesting to see what he says, that any doubling of the percentage of carbon dioxide in the air would raise the temperature of the Earth's surface by 4 degrees. That's within the IPCC range of what we think a doubling of CO2 might give us, so he wasn't far off. Some very basic principles about greenhouse gases and the way they trap radiation. But he goes on to say, by the influence of the increasing percentage of carbonic acid in the atmosphere, we may hope to enjoy ages with more equable and better climates, especially as regards the colder regions of the Earth, ages when the Earth will bring forth much more abundant crops than at present for the benefit of rapidly propagating mankind. I don't think we're quite in that place today with our view on global warming. But of course, there are still some of these aspects of what he's saying which we can relate to when we think about how increasing carbon dioxide in the atmosphere may indeed fertilize ecosystems and so forth. So there's Arrhenius' first prediction of global warming. And now I'm going to step right away around to a different part of the world, to India. Because climate is not just about the basic winds, nor is it just about the energy balance of the planet. It's about the regional behaviour of the weather. And the British Empire had, as you know, a huge presence in India, particularly through the 19th century. And it's here that there was quite a development in trying to understand the regional climate of India. And here's Henry Blandford, who went out there in 1875 as the first Director General of the Indian Meteorological Department. And he got out there and thought, what a wonderful place to finally understand how the atmosphere and weather works. He wrote, order and regularity are as prominent characteristics of India's atmospheric phenomena as are caprice and uncertainty those of the European counterparts. So what was he talking about? Well, he was noting, of course, that in the UK, our weather is always changing. The pressure is going from very low pressures to very high pressures and so on. When he got to India, he saw that actually the pressure was pretty constant a lot of the time. And what he was talking about was actually the diurnal pressure wave that he noted coming past in his barographs. And he also noticed that, of course, the monsoon arrived almost like clockwork on the 1st of June in southern India. So he thought, here I have the perfect laboratory to understand how the atmosphere works, how it interacts with the ocean and the land and the mountains. I can get to understand this because it's a much simpler system. Actually, those of us who've worked on monsoons, as I have, know that actually being able to predict the Indian monsoon is still one of the great challenges of meteorology. In fact, we can forecast the weather in this country far more successfully than we can talk about what is going to happen in India and the monsoon. So, but very soon after Blandford arrived, he was hit by a terrible event, which was the great famine and drought, failure of the monsoon in 1876 to 78. And here we see, just as we do today, the conjunction of politics and climate science. That, of course, the failure of the monsoon and the terrible famine that ensued and the impact on grain harvests and so forth had a huge impact on the British economy. And so the government was very keen to try to be able to control famine through what they called climate prediction. If we could say in advance what the monsoon might be like, maybe we can govern this area, bit of our empire, more effectively. So here we are already, this sense that actually we ought to be able to predict this thing, the monsoon, and work out what it's going to be like, and therefore how we're going to manage the Indian population, food supplies, etc., etc. And Blanford made lots and lots of studies and hypotheses. He talked about the effect of the sun. For a long time, that was quite a favourite. We'll come back to the sun later on. And he talked about Tibetan snow cover. But of course, they were just hypotheses, and he had no way of testing those hypotheses. Of course, now we know that actually that period coincided with one of the biggest El Niños we've ever seen on the observational record. And El Niño has a major impact on the monsoon, and we know that it typically leads to failure of the Indian monsoon. He didn't know that then, we know that now. Move ahead a bit further to the beginning of the 20th century, and here we are with Gilbert Walker, who was the third director. And here we are, he's thinking about how the climate in one part of the world, India, is related to that of another. And even in Blanford's day, there had been correspondence where people had noticed, meteorologists around the Pacific Ocean and into India had noticed that actually the pressure in some stations varied, it seemed, in a way that was coherent with what was happening in India. But nevertheless, here's Walker saying, I think that the relationship of world weather are so complex that the only chance of explaining them is to accumulate the facts empirically. And so this was the birth of statistical climatology, of actually just looking of whether you could find correlations with one part of the world and another. And he was remarkably successful with this. He had, as it says, a human computer. He had lots of people working out correlations of data from around the world. And he introduced the terms the Southern Oscillation, the North Atlantic Oscillation, and the North Pacific Oscillation. Modes of climate variability that we recognize today, but of course, Walker had no way of understanding why these associations existed. He could only observe the climate and all its richness of its variability, but he had no way of understanding it. And it was really only in the 1960s, when we get to Bjerknes, where we begin to start to understand things. And what Bjerknes highlighted was that there is a relationship between the Southern Oscillation that Walker identified through correlations and the intermittent warming of the tropical East Pacific, what we now know as El Niño, that they are closely linked, that the climate is actually a coupled atmosphere-ocean system. And that this thing called the El Niño Southern Oscillation, ENSO, and how that evolves is a fully coupled system. And the impacts of El Niño, which go via the Southern Oscillation, and the changes that that induces on the weather, are part of what drives the impacts of El Niño around the world that we now recognize and can predict. And so, finally, we can begin to understand where these shifts in weather patterns that Walker had observed and had struggled with came from, that the oceans are playing a very integral role in all of this. So here we are in the 1960s with an understanding of how the atmospheric climate works through dynamical meteorology, through radiative transfer. I haven't talked so much about moist thermodynamics, but we'll get on to that. And how what the atmosphere does and how the climate varies around the world is intimately related to what the ocean does. And that these two things, the atmosphere and the ocean, are fully coupled. And to understand the climate, you really need to look at the fully coupled system. So, here we are, back to basics, some classical physics. So how do we understand the climate system? What are the fundamentals? Well, they're things that a lot of us would recognise. Newton's second law of motion, how the atmospheric winds and ocean currents evolve, but a key force for us as meteorologists and oceanographers on a rotating planet is, of course, the role of the Coriolis force. We have something that we call the hydrostatic approximation, which basically balances gravity and the vertical pressure gradient, describes how pressure decreases with height. We have the mass continuity equation, which basically says that if the wind converges, the air rises, and you have to have continuity of mass. And we have the ideal gas equation that relates temperature with density. In other words, warm air rises. Lots of us will remember the ideal gas equation. We have the first law of thermodynamics that links heating to changes in the winds. Heat is work and work is heat. We have the Clausius-Clapeyron equation, rather a mouthful, but that actually relates saturated water vapor pressure to temperature. In other words, warmer air holds more moisture. And you hear a lot of people talk about that when we think about the impacts of climate change on rainfall. It's that equation that just says warmer air holds more moisture. And therefore we should expect more rainfall as the planet warms. And then there are the fundamental laws of radiative transfer, the Planck and Stefan Boltzmann laws that link thermal radiation emitted by a black body, that's typically the Earth's surface, and most clouds actually behave as black bodies, to temperature. And finally, there's Kirchhoff's law that links absorption and emission of radiation by atmospheric gases. So this is the classical physics that's there that underpins climate science. Of course, it's a lot more complex than that, but that's the fundamentals that define so much of how the climate system works. And we can see all of that in action when we think about the energy flow through the system. And this is a very famous picture now from Kevin Trenberth, published in 2009, which just shows for the whole Earth, just in very simple terms, the flows of energy through the system, starting with the energy from the sun coming in at the top, going down through the atmosphere, some of it being reflected back to space by the clouds and by the Earth's surface, and a certain proportion being actually absorbed by the Earth's surface. That's the dominant supply of energy. It is the only supply of energy into planet Earth. But then what happens to that energy when it gets into the planet? Well, of course, it has to be balanced at the surface, and that's achieved by the Earth's surface emitting infrared or heat thermal energy back to space. But not all of that, in fact, very little of it in the end gets right the way back out to space. In fact, if you look at the surface there, a lot of it comes straight back down to the surface due to the greenhouse gases and clouds in the atmosphere. And so, in fact, the Earth's surface is only losing about 60 watts per meter squared of energy through thermal radiation. And so if you think, how am I going to find that other 100 that's there to balance what the sun is giving me? Well, it actually comes through some very interesting things that are all tied up with the weather. And the dominant term is, of course, the evapotranspiration. The planet, the water cycle is absolutely fundamental to the Earth's energy balance. And at the surface, it's the dominant term which cools the Earth's surface. And in so doing, takes water in its solid form, turns it into vapor, and puts it into the atmosphere, where it can form clouds. It can act as a greenhouse gas. Water vapor is our dominant greenhouse gas, and subtly, again, change the energy balance of the system. If we look at the atmosphere itself, then we find that the balance, if we look at it radiatively, what's the atmosphere doing in terms of how much energy is lost through thermal radiation, how much is gained through absorption of of the sun's energy. Those terms show that the atmosphere radiatively is being cooled. How do we get the atmosphere into balance? We do it by condensation of the water that has been evaporated from the surface. So we're effectively transferring heat, latent heat, from the surface into the atmosphere to get balance. And of course, that condensation can be in the form of clouds and rain, and clouds themselves are black bodies, so interact very strongly with the energy flows, as we can see in that diagram. What this diagram hides a lot of is what actually sets up those clouds, what sets up the evaporation, and all those various terms that bring the planet into balance. The final thing to say about that is that if you look at the surface, it's not in balance. This is the current climate. We're out by just under 1 watt per metre squared, and that's because of the imbalance arising from increasing greenhouse gases. Most of that absorbed energy, that heat that's absorbed at the surface, goes into the oceans. 90% of that imbalance is taken up by the oceans that have this huge thermal capacity and take a long time to equilibrate, which is why there is a long-term commitment to global warming through the changes in greenhouse gases concentrations that we've already seen. Very simple view. What does it really look like? Well, it looks like this. So all those flows that I talked about, this is what's really doing it all. And there's, some people say this is Mark Twain. In fact, it's not. But climate is what you expect, weather is what you get. In other words, it is the weather that sets up the climate for the whole planet, moves momentum, moves heat, moves water, all sorts of things around the climate system. It sets up the weather, sets up our regional climates, whether we're in the tropics or whether we're in our latitudes. So let's just have a look at this. What's it showing us? Well, you can probably, if you watch the tropics, see the sun going round. So this is quite fine time scale. So you can see that as the sun goes past, some of the clouds brighten up and then decay, particularly if you watch Africa there and see the sun come past and the clouds build up and then they die down again. And we can see what we would recognize as weather systems going around our latitudes and so forth. And on occasions, you can even see a tropical cyclone. So this is what we're dealing with. This is the weather. And we need to understand the weather to understand our climate. But that's actually not that's not real weather. That's not weather that we've observed. This is weather that's come out of one of our climate model simulations. So when we talk about climate models, which is really what I'm going to talk about tonight, we're talking about that. So these are models that simulate the weather, and they have to simulate the weather because it's the weather that makes the world go round, really. It's the weather that sets up all these energy flows, that equilibrates our planet, that moves heat from the equator to the poles and so forth. And if we can't simulate the weather, then we can't really talk about what the climate will do at any region and how climate change will evolve in the coming decades. So, what are these climate models then that is based on? Well, they're fundamentally the same as what we use in weather forecasting. And the way we do this is we actually cut the Earth's atmosphere up into volumes. Typically for a climate model where the horizontal scale of the box is about 100 kilometers or smaller. You can see what I showed you just now was a 12-kilometer grid square over the whole surface of the Earth, and we slice the atmosphere up into a number of layers of varying depths, and we typically have 70 or more. Our current model has 85. We do the same thing for the oceans. So you have a grid, a set of volumes taking in the whole atmosphere and the oceans, and we do some clever things with the land surface as well. And then we basically take those equations from classical physics that I talked about, and we solve them on that grid. And we integrate the equations forward in time to say how the atmosphere and oceans will evolve as time progresses. So it's a simulation based on fundamental physics, using those equations that I talked about, solving them and some very clever mathematics and how you solve them on a grid that looks a bit like that. Of course, if only it were as simple as that, but it's not, because a lot of the physics that we need to worry about goes on at scales much smaller than the model grid. So they're what we call unresolved scales. And so for that, we have to do clever things of trying to understand the physics that's going on in things like this wonderful picture of clouds and all the different scales that are in that picture, to work out what the cumulative effects of these small scale things are on the larger scale weather that we're resolving with our model. Sorts of clouds that I was showing you in that little movie. And that, of course, has occupied many of us for a very long time in trying to understand how best to do that. And it gets more and more complicated as time goes by. And these days, we not only worry about big clouds like the ones we see in that diagram, but actually what goes on inside a cloud. For example, what goes on inside a cloud when you're in a polluted environment with lots of particles and so forth, and different chemicals that are in the polluted environment, and what they do to the way in which clouds form their cloud droplets, and at what point they they go through that transformation from cloud droplets to rain and so on. And these things are actually at the heart of how the climate system is regulated and how we think that how sensitive the planet is to climate change is to do with some of these sorts of processes that are going on in the clouds. And one of the ways, of course, we can actually have a look at that, and we don't live entirely in model world, so is that we go out and measure things. And I think there is always this sort of myth that climate modelers live in their own little world of their model and never go and look at the real world, and it couldn't be further from the truth. In fact, I always say that in all the work I've done as a climate modeler, I've always started with observations. Whether it's observations of the climate system or whether it's very detailed observations of what's going on in a cloud, for example. This is just a picture of the research aircraft that the UK owns. We share this with the Natural Environment Research Council. The Met Office has had a very long, distinguished history of airborne research over many, many years. And this is what this plane looks like inside. It's full of some really, really clever stuff. And what we're doing all the time is going out and flying through things like clouds, trying to understand the processes that are going on inside clouds, measuring all sorts of things about their properties, and then taking that knowledge and using it to try and improve the way we represent clouds in our models. So our science is continually evolving. These sorts of problems have not been solved and will continue to need very clever instruments, platforms like this, to go out and measure things, observe things, and of course to test other things in the laboratory. Where do we get to? Well, it's quite useful to look at what comes out of this model in terms of a climate. And here I'm just showing you the annual mean rainfall from the observations and from the model. And the colours, the sort of purpley colours, show where the rainfall is the highest. And in observations, we can see, of course, that the tropics is where most of the rainfall goes on. And a lot of it goes on, particularly over the warmest ocean temperatures of the Indian and Pacific Oceans. We can see where our storm tracks are running up the North Atlantic, following the track of the Gulf Stream and so on. And at first look, you'd say, well, this is pretty good, actually. This model's managed to capture a lot of those features, and indeed, it is pretty good. But actually, there are things about it that are still not so good. And I talked earlier about Blanford and his thought that the Indian monsoon was the easiest problem to solve. But actually, if you look at one of the great problems in climate models, is that in the lower figure here, there's nowhere near enough rainfall over peninsular India. And so we continue to have a problem in understanding monsoon rainfall. And yet we can probably do pretty well with rainfall over our neck of the woods. So sobering thought. Still so much to do. But the point here is that actually, I've called this emergent properties. That field comes out of the bringing together of all the weather systems and all the physics that we've incorporated into the model. Of course, climate model development's closely linked to supercomputing power. And I've had the privilege, I suppose, of playing with all these machines on here in one way or another. And here we are with our latest machine here. The access to computed power determines the resolution of the model that you can run, the granularity, the detail that you can afford to simulate. And so we've gone from my early days working on a Cray one here at NCAR, where we had grids of 300 kilometres, to things that we can envisage doing here, where we're down at that 12 kilometre or 10 kilometre scale. It's a huge, huge machine. Some big numbers, 16 petaflops, if you want, sums per second. Huge amounts of memory, huge amounts of storage. This is big science. There is no doubt about this. And yes, it's not all for climate, it's for weather as well, but we use the same models and a lot of the same science to do the climate work that we do for weather. Why does it matter? Well, here's a quick example. This is ocean surface currents from models at different resolutions. And the one that's at 80 kilometres is a classic resolution now that was used in the 5th assessment report in IPCC. In other words, the ocean currents are very, very blurred out because of the lack of resolution. 20 kilometres is our current state-of-the-art climate model that we're now using operationally in the Met Office for our climate change work. 5 kilometres is what we're testing. And these things matter. Look at the Gulf Stream, which is that fine ribbon of high surface currents coming up around Florida, Cape Hatteras, heading off across the Atlantic with all its wiggles. Those things matter for how the Gulf Stream works and how it influences our weather. And that's just not there when you have a model at 80 kilometres. So we need to keep driving the resolution down in our models. The thermohaline circulation, which is part of what regulates the climate of the North Atlantic, and we often hear people saying, will the thermohaline circulation collapse under global warming? Well, when we look at it in detail, it has some really interesting properties. This is a schematic of it, and it shows the formation of the cold water in the seas around Iceland, Norway, Greenland, these currents that come down through the Denmark Straits and the various overflows at depth and form the flow of the Atlantic thermohaline circulation southwards, which returns eventually as a warm, salty flow up through the Gulf Stream and gives us the mild climate that we enjoy in the UK. The question is, how well do we need to resolve these flows to understand and predict what will happen to the thermohaline circulation? Well, these things are really important. And again, when we look at what these different resolution models do, and we look at the observed ocean flows versus model resolution, we can see so clearly that resolution really matters to get the right flows down these deep overflows, the right drivers for the Atlantic thermohaline circulation. So all the time we're learning from these models about how the system works and how the models need to be constructed to answer really key questions. Of course, they are our laboratories. And like any scientist, I want the best laboratory I can get my hands on, which is why over the years I've argued that we need bigger supercomputers, because essentially that's what gives me the laboratory. We can't perform experiments on the real world, except perhaps the one that we're performing now, which is to shove lots of carbon dioxide into the atmosphere. It's an experiment, and we're seeing what's happening. But we can test all sorts of hypotheses. We can actually pull apart the system, and we can do what-if experiments. So here's an example, very quickly. We had a cold winter rather unexpectedly a few years back. And the question was, well, was that something to do with the sun? So here's the sun's 11-year solar cycle. And what we can see here is that around the time of that very cold winter, we were in a very deep solar minimum. So we tend to think, well, you know, the variations in the sun's output are incredibly small. How can that have really anything to do with our climate? And yet, the observations were telling us just that when we looked at changes in pressure and temperature between solar min and solar max, what we could see was changes in the pressure distribution such that we have a greater prevalence of easterly winds over the UK in winter. A very characteristic pattern of very cold over Europe, warm over Greenland, higher pressure than normal to the north, lower to the south, and easterly flow. But why? How do we understand that? And is it really to do with the sun? Or was there something else going on in the climate system at the same time that's just happened to give us that pattern? Remember, we haven't seen many 11-year solar cycles in the time that we've got observations. But we can look at it in a model. So we can impose the solar cycle on the model, and we can look at what the model thinks is the difference between minimum and maximum. And at that time, some really interesting observations were coming out about the sun's output. That as you go through the 11-year solar cycle, yes, the total energy from the sun barely changes, but actually the amount of ultraviolet radiation from the sun changes quite a lot. And so we hypothesized that that was the reason why we get this particular climate response as you go through the solar cycle. And we could test it in a model. And this is what we got. So we got that signal of higher than normal pressure to the north, lower to the south, easterly winds. Not such a clear signal of cold to the east, but it's there. And you could start to unpick what was happening in the model to give you those signals at the surface. How do you get there when we're talking about ultraviolet radiation? And of course, how you get there, of course, is that the ultraviolet radiation interacts with the stratospheric ozone layer, alters the stratospheric circulation, which propagates downwards to the surface. And so here we are, we have an explanation through the use of a model as a laboratory to understand how variations in the sun can affect our local climate in the UK. Without a model, we could not have done that. Now, of course, this is not just about testing this particular thing, but actually if we found the mechanism and the model is reproducing what we observe, then we think we have a model that's fit for purpose to tackle some other big questions about the sun. And one of those was the question about, are we leaving a grand solar maximum? So here we've got a record of sunspots back to 1700. And one of the big questions as we came out of this last solar minimum and went into a maximum, which has been very muted, was whether in fact the sun, which has these much longer timescale variations, were coming off this grand maximum which we've been in for the last 100 years, and maybe going into a much quieter period of the sun in the future. And what would that mean? Well, we can actually, of course, knowing that the model can respond realistically to variations in the 11-year solar cycle, we can also ask the same question about coming off a grand solar maximum. And this is what you might get if we did indeed have a less active sun within the next 50 years. That you do indeed see just what we've seen for the 11-year cycle. It's the same process, colder over Eastern Europe and so forth. It's not large enough to cancel out global warming, and that's an important point. That we don't believe that the sun will get us out of the problem we're in. But it also says very importantly that cold winters may not be a thing of the past. This is an average, but actually how it will be manifested is through cold winters when we're into solar minimum. So here we are being able to do what-if experiments. And here's what I think is one of the most famous graphs around, which is the Keeling curve. There's Charles David Keeling, who started these measurements in Hawaii in the late 50s. And he noticed that actually the carbon dioxide kept on going up year by year. I started in the Met Office in about 1973. And at that time, we had the first paper, what-if paper, from Manabe and Weatherald, one of the seminal papers looking at the effects of doubling CO2 concentration on the climate of a general circulation model. So we weren't very far up that Keeling curve at that point, but this was a what-if. What if we really are heading, as those very early measurements suggested? And you can see that he says for a doubling you get 2.93 K warming. Again, within the IPCC range. Remember Arrhenius said 4, he's saying 3. And lots of the other things that they noticed in their climate model simulation are things that subsequently we have observed as part of the changing climate. I wrote something fairly similar in the late 70s, looking at slightly different things about doubling CO2. I'll be honest, at the time, I thought it was an interesting academic exercise. I had no idea what the implications of it would be. But now, of course, we know that the human influence on the climate system is clear. And we see lots of things in the observations that actually Manabe and Weatherald were pointing out in their paper in the 70s. But of course we can detect those things, but are these changes really due to us? And this is where what-if experiments come in again. We can do the world that would have been without greenhouse gas emissions. And as an example, let me take European summer temperatures. What we have here in black is the observed record of European summer temperatures. A very stark example of global warming, which has gone on in an unremitting way right through the apparent pause in global mean surface temperatures. In Europe, summer temperatures, the warming has continued apace. And then we have two envelopes of climate model simulations where we're actually just looking at the natural variability in the climate system, the envelope of what could possibly have happened. We have a red set and pink set, which uses the greenhouse gas concentrations that we've observed. And then we have a green set, that's the world that would have been if we hadn't been increasing carbon dioxide and other greenhouse gases. And what we can see here very clearly is that the observations are no longer captured by the world that would have been. It's very clear that what we're doing by increasing greenhouse gas concentrations is leading to that change in European summer temperatures. And indeed, at least for European summer temperatures, the observations lie at the upper end of what the climate models are saying, which is also interesting because we often get told that the climate models are biased too warm. And that's based on global mean temperatures. When we look at things that really matter to us as individuals, that's not necessarily true. We need to be very careful not to throw the climate models out because we think they run too warm. And of course, we can actually then say, well, how is the landscape of risk changing because of climate change? And in Europe, we can look at the heat wave we had in 2003 and say that the risk of that has at least doubled because of our activities. We can now increasingly do that for many extreme events around the world, and each year now the international science community publishes a bulletin looking at extremes from the past year and asking the question, was there a role from climate change in the severity of those events? And the numbers keep racking up. Just a few here examples. And even for ourselves here in the UK, whilst we haven't done this year's floods, the floods from 2 years ago, we have done a formal attribution of the contribution of climate change. So the evidence is stacking up. So there's no doubt, I think, that we're taking the planet into uncharted territory. The Keeling curve that I showed earlier of CO2, we started pre-industrial revolution at 280 parts per million by volume. We're now over 400. That's a lot. Remember that 280 was the highest concentration that we've observed for at least 800,000 years. So this planet is being changed rapidly and in a very dramatic way. Those numbers are large, those differences are large. And the challenge for us now as modelers is, and as scientists, is to try and answer some of these really difficult questions. Do we know what level of climate change could be dangerous? Can we provide society with a roadmap of where we're going? Not just about changes in the global mean temperature, but actually about the variations in our weather and our climate in the context of a warming world. Can we help to make society more resilient and better prepared? Forewarned is forearmed, as they say. And what should society do to mitigate and adapt to climate change to avoid its worst impacts? The sorts of science that we do with our models is the evidence that informs investments that, say, the UK government is going to make in flood defence is running to £1 billion or more in the next few years to protect us against flooding. It's vital that we provide the evidence base against how those investments will be made. And we know from the work that we do that actually we need to act urgently to deal with climate change, because our models and the interpretation of what those models are saying tell us that the impacts at 4 degrees C, global warming, will be more than twice those at 2 degrees C. These impacts rack up quite significantly the greater the warming that the planet experiences. And we can avoid a lot of those impacts by staying within 2 degrees C, which is why Paris said we have to find a way to stay within 2 degrees or even lower. But we have a challenge on our hands for that. Here's I think, one of the most important figures that came out of the 5th assessment report that relates global mean temperature rise to the cumulative carbon emissions. This is really important. It's about how much we've emitted since we started this grand experiment with the planet, since the Industrial Revolution. And that's because carbon dioxide has such a long lifetime. And it's a very simple relationship, and the observations show that, between temperature and cumulative emissions, quite a simple relationship. And we can see how we can follow up those curves depending on what we choose to do. If we do nothing at 2100, will be at nearly 5 degrees. If we do everything we can, we may just stay below 2 degrees. And so we can see here, there's the 2 degrees, there's the 4 degrees. That's the budget that we're allowed. 790 gigatons of carbon is our allowable budget. But we've already emitted 535 of that. So we're halfway to 2 degrees. This last year, global mean temperatures went to 1 degree, but we've had 2/3 of our allowable carbon budgets. But more than that, the latest science that we're doing in the Hadley Centre at Met Office, looking at other processes beyond just the physical climate system that I've talked about, other things that could go on. One of them is the melting of the permafrost. Another one is the efficiency by which the natural carbon cycle, ecosystems can take up carbon, is actually constrained by nitrogen. These are quite complex systems, and we're gradually beginning to understand them. And we think that actually the carbon cycle will be quite limited by the availability of nitrogen. When you put those things into the models, then you find that actually our allowable budget shifts back even more. And for a 2-degree world, we probably have about 100 gigatons of carbon less than we thought we had. This is new since the 5th assessment report. So we have what I call is a defining problem for the 21st century. So let me just recap on climate models. Let's not forget they're based on fundamental and immutable laws of physics. They're not just made up in our heads. They're not empirical models. These are based on physics. They are incredibly complex. They're amazing. One of the most amazing developments, I think, in the last few decades, these incredible codes and what they can do. They help us to do so many things, to understand how the climate system works, understand why our climate is changing, and as important as ever, I think more than ever, to see into the future. I'm going to take a step back into the 19th century and the wreck of the Royal Charter on the cliffs of Anglesey in 1859. And you might say, why is she showing this? Well, 450 lives were lost in this wreck, and there were other ships wrecked at the same time. And that was because nobody knew the storm was coming. And after that event, Robert Fitzroy wrote to the Times, and he said, "Man cannot still the raging of the wind, but he can predict it. He cannot appease the storm, but he can escape its violence. And if all the appliances available for the salvation of life were but properly employed, the effects of these awful visitations might be wonderfully mitigated." Well, following the wreck of the Royal Charter, Fitzroy set up a whole system of barographs around the UK coast, and he started the first shipping forecast so that there were storm warnings out so that ships could have a sense of what was coming. He became the first head of the Met Office. The Met Office was founded by Fitzroy. He, of course, was also the captain of the Beagle, and he took Charles Darwin on his voyages around the world. He was a great man who sadly in his lifetime was ridiculed for his weather forecasting. But he speaks to us across the years, in a sense, because if he could see the sort of forecasts that we make today and the way in which they save lives and livelihoods and so forth, and if he was posed with the sort of problem of climate change that we're posed with, and the sort of things that we can do so that we are have the appliances available to us for the salvation of our lives, our economies, our social structures, our cities, whatever, our food security, our energy security, our water security, then being forewarned and forearmed in what climate change could mean for us, mean that the awful visitations that might come our way might be wonderfully mitigated. So, thank you for listening. We have, as you can see, Lots of science still to do. One of the great challenges for the 21st century to address. If you want to read more about the sort of science we get up to, you can find our new science strategy on our website, Delivering Science with Impact, and you'll find Fitzroy inside the front cover, as he's just where he ought to be. So thank you very much.
Do you attempt to simulate physical geography and vegetation?